Okay, so here is the next question, and of course, our next question, highly intuitive, and it says, a nursing mother, prepare her baby's milk at 85 degrees Celsius in a feeding bottle in order to cool it down to 40 degrees Celsius. She immersed the bottle in an aluminum bowl of heat capacity 90 joules per Kelvin, containing 500 grams of water at 26 degrees Celsius. If the mass of the mixture is 300 grams, calculate the heat capacity of the mixture. Neglect heat losses and heat capacity of the bottle. SHC of water is 4000 joules per kilogram per Kelvin. So in order to calculate this, what we need to do here is a nursing mother prepares her baby mix at a mixture of 85 degrees Celsius. So what we know about this is that temperature of the baby's milk, theta MB, which is temperature of the baby's milk, that's 85 degrees Celsius. In a feeding bottle, in order to cool it down to 40 degrees Celsius. Our aim is to take the temperature from 45 degrees Celsius down to from 85 degrees Celsius down to 40 degrees Celsius. So of course that should be the final temperature, and the final temperature is 40 degrees Celsius. She immersed the bottle in an aluminium bowl of heat capacity 90 joules per Kelvin. Now the heat capacity of the aluminium bowl is 90 joules per Kelvin, so we can take the heat capacity of the bowl. Of course, I'm just going to call that one B, is 90 joules per Kelvin. That is 90 joules per Kelvin. And what else did you do here? Containing 500 grams of water, and then we can say the mass of water is 500 grams at 26 degrees Celsius, and that will be the temperature of the water, and that is also equivalent to temperature of the bowl, and that is equal to 26 degrees Celsius. Okay, so here the mass of the mixture, which is the mass of the milk, mass of the baby's milk, is 26, is actually 26, the mass of the baby's milk is 300 grams. So there we go. Now to solve this question, here, what do we need to do? First, we need to calculate. In here, we are looking for the specific heat capacity of the mixture, right? And to do this, there is always an idea we use for it, and that is to say that heat loss is always equal to heat gain, right? That is, the quantity of heat loss is always equal to the quantity of heat gain. Now if you look at it, the baby's milk definitely lost heat. It got to move down from 85 degrees Celsius to 40 degrees Celsius, right? And of course the aluminium bowl, right, and the water gain heat, because in that hand they go from 26 degrees Celsius to 40 degrees Celsius, and we can make this calculation work immediately, right, by taking this by saying the quantity of heat lost is what we want to calculate, and to calculate the heat loss, right, is going to be the mass of the baby's milk multiplied by the specific heat capacity of the baby's milk multiply by the change in temperature. And of course, to do this, we can go ahead and say the mass of the baby's milk is 300 grams. That will be divided by 1000 multiplied by the specific heat capacity of the baby's milk, that is what we're looking for, multiplied by the change in temperature of that baby's milk. It went from 85 to 40 degrees Celsius, and that's 85 minus 40, and this will produce 0.3 times specific heat capacity of the baby's milk, multiplying that straight away by, that will give us in here 85 minus 40, and that produces us with 45, and we can take that 45 and multiply by 0.3, and that's giving us 13.5 specific heat capacity of the baby's milk. Okay, so that we get, and from here we can take the heat gain, and that will be gain, the quantity of heat gain. Now in this end, we know that the water gain heat, right? And we can calculate the specific heat capacity of water, because in this case she immersed the bottle in an aluminum bowl of heat capacity 90 joules per Kelvin containing 500 grams of water at 26 degrees Celsius. We have to calculate the mass of the mixture. Now two people gain heat here. The two people that gain the heat in this case is the bowl and also the aluminum bowl, of course, also gain heat. So in this end, and here we have to neglect the heat losses, and we have to neglect heat losses and heat capacity of the bottle, that is the bottle of the baby's milk. So we are not to consider the bottle of the baby's milk, but to consider the content of the bottle of the baby's milk. So in this case, I guess we have to take some quick calculation, right? That we have mass of water. We are calculating the heat gain by water now, times the specific heat capacity of water, multiplied by the change in temperature for water, right? In case you do not remember that two people actually gain heat under here, right? So there's a heat gain. There is a heat gain here. So there's a heat gain here. There's a heat gain in that case by water, and of course there's also heat gain by the bowl. So let's calculate the heat gain by water first, and that will be equal to the mass of the water where it was positioned is 500 grams, and that will be 500 divided by 1000 multiplied by the specific heat capacity of water, which is 4200, into the bracket of, now since water gain heat, it has to move from 40 degrees Celsius. It's moved from 26 degrees Celsius to 40 degrees Celsius, so it's going to be 40 minus 26. So of course this will produce 0.5 multiplied by 4200, and that will give us 40 minus 26, and that will give us 14 straight away, and we can multiply all the value by 0.5 and by 4200, and that will give us 29,400. 29,400, right, joules. Okay, and right on the second scale here, we can calculate the heat gained by the bowl. This is for water, and then we can calculate out of the aluminum bowl now, AL bowl, which is the aluminum bowl